Okay, so today we have an important step in the physics of the neuron. So we had looked at the neuron and had looked last time at the dendritic part of the neuron, where the neuron integrates signals that it receives from other neurons through synapses that contact the dendrites of the neurons. So here are the dendrites, and this information is collected by the neuron, and this is described by the cable equation. V of x and t is equal, dt is equal to lambda squared divided by tau times the second derivative of v minus v, minus 1 over tau v. And so this is a diffusion equation where the diffusing substance had a finite lifetime. And that collects data. The individual synapses can add positive and negative contributions to V that is measured relative to the resting potential of the cell. And the diffusion leads then to propagation of voltage to the neuron. And at the beginning of the axon begins a part of the neuron that is acting very differently. It doesn't act passively. Here we have basically a diagram that characterizes the behavior of the neuron or of the neuronal membrane. Where the different ion types have voltage-independent conductivities or resistances. So we have an inside and an outside of the neuron, and so we have in the membrane the conductivities that are fixed. So maybe I replace them maybe by an average value. So it was a G missing, so an average value here and here. So these conductivities are not changing in time. They are not. They don't have a dynamic variable that alters them. But in the axon, we have different behavior. In the axon, we have the behavior that is described by this kind of diagram, circuit diagram. Namely, I don't want to draw all the details here. I don't write the labels anymore. They're just the same as in the other diagram. But these conductivities here, except for the one for the remaining ions, these two for the potassium and for the sodium ion, these conductivities are changing in time as a function of the voltage. So G, K is a function of the voltage, and G sodium is a function of the voltage. And that gives rise to dramatic different behavior, to a threshold behavior that produces then here in the neuron a signal that looks about as follows. And this one here is a rise of G sodium, and this is a rise of G potassium. We had seen that the voltage equilibrium potential for neuron can be written as sum over G alpha E alpha divided by sum over alpha G alpha. And when you look at this expression, then you will recognize that if one particular conductivity is dominant, then E0 assumes that particular E alpha value. And we had an E alpha value of sodium that was, I think, I don't know what, I forgot which one is 115 and which 120, but it's sort of plus 120 for sodium, and it is minus 120 millivolt for potassium relative to the resting potential. And so when we increase the conductivity of sodium, we are going to increase the voltage, because the equilibrium, the resting potential is increased and the voltage follows. And other way around, if we increase conductivity of potassium, then the potential goes down as E0 goes down, and then the voltage follows. And here we have then an invariant shape that either we are getting this kind of behavior when we are going above a threshold. Let's say here's a threshold, and if we go above the threshold, we are doing this one. If we stay below the threshold, if this is a threshold, and let's say this is our resting potential, we go like this, we decay back, we go like this, we decay back, we go here, we decay back. But when we go here, we are making a signal. So here we have below the threshold, we have relaxation, and above the threshold we have signaling. And the signaling is always the same, looks always the same. It's not like sometimes strong and weak, or there's not an analog value in the sense of the word analog, meaning continuous. And so we have this very important difference in the behavior. And so then the neuron ends up in sending out itself dendrites at the end of the cell that contact through synapses other neurons and communicate to other neurons. So we have here then the signaling section, and this is a digital response. So it's an all or nothing response, and then here we have then a distribution that is again passive, and that tells in other cells that a signal came and talks to them through synapses. And so here we have this very different kind of behavior that we are talking about today. And this point is have a special name, but it is in a way not different from any other point here. This is just the place in the neuron where the membrane becomes an active membrane in regard to its potassium and sodium channels, and it assumes this threshold behavior with a digital response to the voltage of the cell. And that's what I want to quickly show you, these channels. And so when we turn, maybe we can turn off the light, and then I can show you these pictures. Here we have the typical nerve cell. And so we are getting input from the dendrites, and then we have here an axon that is a signaling element. It branches here actually, so it's not quite as simple as I put it there, but in principle that's how they look like. And so this behavior develops in the membrane of the neuron, where the ion channels sit. And here we have ion channels that have a fixed conductivity in the dendritic part, and in the axonal part we have ion channels that have a variable conductivity. Here you see the measured pulse, and you see here that the increase, the decrease, and then the return to the resting potential. And you see here the measurement of the contributing conductivities. In green is the sodium conductivity, in blue is the potassium conductivity, and in purple is then the resulting voltage. And in red is, I think, the sum of the conductivities, but that's not very important property, because some ions go in one direction, the others in the other direction. So this is a very famous measurement that was discovered and described, and it was also cast into a mathematical description that was at the time totally phenomenological. However, it fitted very, very well the behavior of typical quote neurons, that it really was given a degree of reality that that even led to the Nobel Prize of people who were involved here. Katz got the Nobel Prize for the physiology, and Hodgkin and Huxley got it for studying many neurons and realizing the mathematical pattern behind this behavior and casting it into a form of equations. So I don't want to go through the equations now because I write them down in a second. It's better that I do that later. So here we have now the channel. So this is a potassium channel. It sits in a membrane, and it has two parts. It has a part that is the actual channel with an opening and closing compartment. That is what the name says. It opens and closes a channel. The channel itself is extremely selective for potassium ions in this case. They are selected over sodium ions to a very high degree, namely the factor of 10,000, and that belies the difference of sodium and potassium. These two ions have very similar van der Waals radii, so they really don't have a big difference in thickness. The main thing what the channel actually exploits in order to differentiate is hydration energy differences between sodium and potassium. There they are different enough so that the channel peels the potassium out of water more easily than the sodium, and let them pass by a facilitating factor of 10,000. And now the channel is surrounded by further membrane proteins that are connected here through helices that are the critical element. This is a so-called F4 helix. And here we have what I call the voltage gate. This is the part that is actually sensitive to the voltage across the membrane. So the channel in the middle is passive, and some of these channels are in fact completely passive because they do not contain the voltage sensing domains, here shown in red and in gold. So you just don't have them, and then you have an average conductivity fixed in time. But these ones being added, it looks now that these channels are symmetric, dimeric, they have a twofold symmetry, but in fact they have a fourfold symmetry. I just don't show you here the one that is in front and the part that is behind to just make the figure simpler. But it's a fourfold symmetric channel. And each of these channels have the helices S6 and S5. They are here shown in blue and in black. They make the central channel, the passive part. S4 is the connecting helix, and S3, S2, S1 are the helices connected with the voltage sensing domain. This is then the voltage sensing domain part. So I show you a little bit more this in detail by rotating it in front of you, now with all four of them. Here you see the fourfold symmetry from top down. And so now we have four of them, and you see how they're connected with this helix S4. And you can imagine that they do their job. These domains, that they can sense a potential and open and close the channel by just pulling it open or letting it close again. So if we now look a little bit closer to the channel, then we see in the middle the passive channel. And you see here two ions that are two potassium ions that sit there conducting through the channel. Sometimes you have two, sometimes you have three, rarely you have one. They are conducted by what is called a knock-on mechanism, that one ion comes from here and knocks the last one out. So if you have two in here, then one comes and this one leaves and it's replaced by two. Often you have three in there, then the one goes out and three are there. So this is a little bit stochastic. There are preferential points for the ions, and they are sitting here in a region that is very conspicuous. Here you see alpha helices that we had encountered when we looked at the structure of proteins. So there are secondary structure elements, the alpha helices and the beta sheets. I very briefly introduced to you. You met them several times when you did your case studies. Here we have something that is actually what you call an inverted alpha helix. So now I have to appeal to some intuition that most of you will not have, because you are of an age that you never experience much the telephone cable of all days, when we had at home telephones that were actually had the speaker connected to the base of the telephone through a helical wire. The helical wire made the cable shorter, but you could extend it a little bit so that you could get up out of your chair, move a little bit around. Now if you would have taken such an coiled up wire and you would have now rotated against the helical pitch that the wire has until it becomes straight, then it's actually not really straight. You unwound it, it then assumes sort of a helical pitch with the opposite sense, namely like you see here. And that will take you considerable energy to do that. And that takes considerable energy to the protein structure to invert a normal helix to an inverted helix. And there must be a good reason. And the reason is that this helix interacts all with 1 plus 4 through hydrogen bonds to stabilize the helix. And 1 plus 4 and plus 4, those are the amino acids that form hydrogen bonds at the peptide backbone, not with the side groups, but with the backbone of the peptide bonds, where the polymeric form of a protein is particularly stiff and stable. And when you invert the helix, then this stiff part that is usually inside of the helix, to the outside radiates the side groups in a helix. So side groups are just like a Christmas tree. They go left and right and front and back. But when you invert the helix, then here you have in this direction towards the ions the backbone part of the protein structure pointing toward the ion, the stiff part of the protein structure, the very stiff part. And so here you can now define a very, very precise structural element that is so precise that it can select potassium ions over sodium ions by a factor of 10,000. So you reach this one through a very costly architecture. So this one is high energy region of the protein that is compensated at other places in the protein, so that the overall energy is favorable, but this particular piece is unfavorable. But it does this very important function of selecting for this channel only potassium ions. Okay, so this is the passive part, and we can have a closer look at it to see how these things look like. You see here one with 3 ions in there. Here, so this was actually given a Nobel Prize for exactly 10 years ago. Here you see 3 ions, and you see this inverted helix. And I mind you that it's actually 4-fold symmetric, but I only show 2. And so now you have the knock-on mechanism. When the bottom comes, the top one flies off. And here you see an actual trajectory computed with a simulation. And so you see there that you see the ion comes, the other one leaves already. And then after a while, the new ion integrates itself into the thing. Even the second one leaves under these particular conditions. But you see in principle how it works. So this is a passive component. And now we look at the active component, the voltage sensing domains. So we see them here in brown. And here we see a single one. And we see here the sequence, the voltage sensing domains of various types of organisms. You find them actually even in bacteria. Even bacteria have a reason to sense their voltage and open and close channels. So they are quite widely distributed. And key in understanding the function are charged amino acids that are found inside of the membrane. The membrane is aliphatic, hydrophobic. It doesn't like charges, but in this part of the protein that is regulating the conductivity, you find 4 arginine put together there, they are positively charged side groups. You see them here sticking out. And they are part of an alpha helix, and they are arranged from one to the next with a step in the amino acid number of 3 rather than 4. So they are not along one line of the helix, but they go around because they are too closely spaced. But these helices, I mentioned this already to you earlier, can actually exist as 1,4 helices, that's a typical one, but also as 1,3 helices. And this is a transition that is being exploited by these channels when they switch between the open and the closed state. So the open and closed state had a functional difference of the S4 helix that you see is one time pointing away from the channel, from the passive channel, and one time towards it. And this is a lever with which you open and close the channel. So this is a functionally important thing. But the helix itself is not voltage sensitive. It gets its information from this helix that rotates itself from a 1,4 to a 1,3 helix. And that is the key trick. And if you now look how these charges are distributed across the membrane, then here we have the z-axis along the membrane. The membrane goes from -20 to +20. And you see that the voltage drops in the channel not linearly, like from -20 to +20, but it drops very suddenly in the middle. That's not a big deal for a physicist. It just tells you that this is where there must be some water. The dielectric constant must be higher. If the dielectric constant would be constant everywhere in the membrane, you would get a linear dependence, very easy to calculate with the laws of electrostatics. But if you have different dielectric constants, and here you have high dielectric constant and here very low, then the potential only drops in the high dielectric constant part. And now you see that that is actually a part where the membrane is here maybe, let's say just 0, and here is just, about 10. It's a little bit more than 10 angstrom, let's say 12 or some angstrom. And now you see that in one form we have these charged amino acids all clustered here, whereas in the other form we have them more clustered on the bottom. Not completely they're clustered here, but you see clearly a shift of the charges over a very small distance. The distance is only about 10 angstrom from here to here. So we go from this center cluster to this center cluster. Center is here, center is here, okay, maybe 12 angstrom. We shift the center by 12 angstrom, but with a huge effect on the energetics, because this is a potential drop. And here we are dropping the potential very, very rapidly, and as a result, we are getting a strong coupling to the voltage. So if we have a strong voltage, we shift them. If we have a weaker voltage, we don't shift them. So this was a big mystery. How can you shift charges in a voltage of, like 50 millivolts or something? And when you do the calculation and you assume that the voltage drops all across the membrane, you end up with not enough force that could drive such a channel. But when you now build in the dielectric properties, then you're getting this detail nicely accounted for, and you see that yes, the potential actually drops only over 10 angstrom, and you can move these charges quickly over this short distance by twisting the helix from a helix with a 4 repeat to a helix with a 3 repeat. And at the same time, you are turning actually this reordering into twisting motion that you connect with the helix and that pulls just like an iris on your camera that pulls the channel open and closes it. A real impressive invention at the molecular level. So this is how it does, and now we have a similar channel that is not yet so well understood because the structure was only solved recently, and it's also only a bacterial channel, but we also know the sodium channel. The sodium channel looks very similar. It doesn't have the detail of the selectivity that we find in the potassium channel. It also is selective, but it's different. We don't have these inverted helices, or at least it looks all very different. And so this is still open up for grabs for graduate students to study. How do you develop here the selectivity? You also surround these channels by voltage sensing domains that are very, very similarly structured. They also have a linker. And so that part works very similarly. They are very homologous, so they have one more helix than the other one. So there are 4 helices here plus the linker helix. But otherwise, they look very similar. So this is really just a new structure that is now being studied, and somewhere in the world, probably a graduate student is already jubilating because she or he got some nice results explaining how this channel actually does its job of selectivity and voltage gating. So this is the basis. Can we now turn on the light again? And now we want to study this. So we have already all the ingredients here. Namely, the effective circuit diagram that translates now into an equation. We now first look at the equation by putting a copper wire all along the axon so that the voltage is everywhere the same. So we have homogeneous voltage. And then next time we will talk a little bit about how we are, just like in case of the cable equation, can diffusively couple the voltage along the axon so that it moves along. And so we just have now a homogeneous equation, and that equation reads C dV to dt is equal, and now we are getting 3 elements of currents. The last one, okay, let me write it here. So, and I told you already that this one is sort of the boring part. This is a very small term. This is a small conductivity. We will not consider that much further. But here we have something interesting. We have, for the term GK, actually an independent part, a constant part of the conductivity, times a part that is voltage gated. And what I write to you now is the Hodgkin-Huxley equation that was formulated in the 50s and 60s, way before there was anything known about the ion channels. So now you saw the ion channels, and we sort of cheated relative to Hodgkin-Huxley, who only knew the electrophysiology of the neuron, but they didn't know how things came about. Pretty sure they must have discussed among themselves and with their students that there could be ion channels in there, but that was totally hypothetical. But they played with it, and they said there's a term that appears in the force power. And then they said that for the sodium conductivity, we're getting a constant factor times the term that goes with the third power and the term that goes with the first power. So here we have a fourth order term, and here we have a fourth order. So here we have a fourth order polynomial, but mixed. Now, if you think of this potassium channel that I showed you, then this is very interesting, because what is very likely the case is that our central channel is surrounded by voltage sensing domains that are each acting independently in opening and closing. And if this is the case, there is sort of like they do their probabilistic work, they do their probabilistic work, then all together, it's like, what's the probability of throwing each with a dice, with 4 dices and 6 eyes? It is 1/6 to the fourth power. And so here we are getting the fourth power. If they would act independently, which apparently they do. They didn't know about tetrameric ion channels. They just had this. And some people were trying as usual, oh, maybe there is also higher power involved, we need some additional terms. But Hodgkin said, no, yeah, this is all detailed. What you are talking about is not really the essence. The essence is this term. So how does nature do it? Nature is doing it by making the channel of 4 independent elements. So when you are building the channel, then the building block is this element. Here you have 2 helices, namely S6 and S5. That makes a central channel, and helices S1 to S4 make the voltage sensing domain. And so then you get automatically this behavior, that you have an n to the 4 term. The n to the 4 terms has its own dynamics, and it's described by this equation where we have an alpha of v times 1 minus n plus a minus beta of v times n. So this is an equation that describes it according to Hodgkin-Huxley. This equation they wrote down, where they told us what alpha and beta is, and those are the alphas and betas for the variable n. Now we would say, oh, these are the alphas and betas for the voltage sensing domain of the potassium channel. And you can write this equation as n dot is equal to n infinity. I have to look it up. I should not have to look it up. So I write it like this, where we now say that n infinity is equal to alpha v, alpha nv, divided by alpha n of v plus beta n of v, and tau n, tau n, but here's 1 over tau n is 1 over alpha n of v plus beta n of v. So if you do this, then I'm pretty sure it's correct. You can try it out. Okay, so this is how it goes. And if you now look at the solution, then the solution goes as follows: that you have here the initial value n0, and here you have n infinity. And when you start from n0, you're going exponentially towards n infinity. This is time. With the decay time, this goes like e to the minus t over tau n. And so this 1 over alpha plus beta gives you the time constant. And the n infinity value that you assume is given by the ratio alpha divided by alpha plus beta. So they determine how much openness you get, how open these channels are. That is actually how we define it. If n goes to 1, then these are all positive numbers, so the most it can be 1. If it goes to 1, then it's always open at that voltage. And if it's 0, then it's never open, and something in between. So that's what they got. Then they had this other term. This term looks a little bit puzzling because you cannot build the channel the same way you build this channel. When you are making a channel from 4 independent elements, you're getting a n to the 4 term. But they got this term. How can they possibly get this term? Now, we can look at this channel in the following way. So we can look at the potassium channel as F1 to S6 coming from this unit. So I call this one S1 to S6. We connect it to a second S1 to S6. We connect it to a third S1 to S6. And we connect it to fourth. Now, since they are all the same, nature doesn't really have to put them together. You can just put them independently. They build the channel. The result is an n to the 4th term. If they act independently, statistically, and apparently they do. That will not be totally correct. This is all these people who said, oh, maybe we need more powers and modification. How they're probably right. There is a little coupling between them, but basically that's how it is. Now for the sodium channel, we would expect we cannot do that. So for the sodium channel, we need to put things together like this. And in fact, that's what you find. The sodium channel is 4 times as long, the gene, as the one of the potassium channel. And so here we have then, more helices, so we go from F1 to S7. But here we have type 1. Here we have type 2. Here we have type 3. And here we have type 4. Except that these guys here are very similar. They're not identical, but they're very similar. And this one is different. So then we are getting right to this one. So now we have, in the Hodgkin-Huxley theory, the same kind of equation, except with a slightly different alpha and beta functions for m dot and for h dot. And so now we are getting then this kind of behavior with this kind of conductivity. So that's how you do it. So you see how evolution plays its game by one time using 4 independent monomers and one time putting 4 together into one unit, thereby controlling the composition to make sure we are getting a 3 and 1 composition rather than just an n to the 4 composition. And then evolution made these guys very similar and this one different. Now it's very interesting what the difference between the two is. It's the following, that this guy is actually a friend of these guys. And approximately, there are such good relationships that H and N arise almost with the same value. There's a little constant there between them, but they are, N and H, they are moving the same way. Let's say go to the Olympics, you have here the ones that are the moving same speed as this. Turns out these guys here are much faster than this one. As you may recall from the picture I showed, that the sodium current had the conductivity rising very, very quickly. So these are the gold medalists. Gold, silver, bronze, but very close. They almost came through the same millisecond across the finishing line. So they are very, very they are very similar, very fast. In fact, they are so fast that you can replace m by m infinity. They did already just like this. What is this guy, the bald guy there, who is already done, did his 100 meter when the others are just starting. They're already done very, very quickly. And so in doing this in solving this equation, we can replace here this one by infinity approximately, and we are not getting really screw up. And then these guys here are very good friends, so we can put this one an n. You know, we have to maybe modify a little bit to put some little constant there, but okay, we shift this value a little bit to absorb that one. So if we do this one, then we have now Hodgkin-Huxley equation with one variable and here a second variable. So the Hodgkin-Huxley equation looks like a little complicated equation, differential equation, non-linear with a force power. Ooh. But in fact, it lives in a two-dimensional manifold. It's not exactly a linear space of the variables, but it's basically two-dimensional, and all the dynamics take place in essentially two dimensions because m is very quick, and h and n are related to each other. They are just going in so much in parallel that we can just tell them, okay, it's the same. So if you want to understand the Hodgkin-Huxley equation, it is sufficient to just look at this sheet. And then, of course, we stretch it out. And now we have here new variables, x1, that is about the variable v, and x2, which accounts for the variable n. Thought of it, maybe I should rather make it a function of n, because it's not quite linearly related to it. So that is what we get. And so now, this is actually important. First, when we think about it, we have a situation that Hodgkin-Huxley in the 50s and the 60s measured these neurons, and they found this behavior that I described, this threshold behavior. We will get it at the end out of our analysis, but at this moment you just have to take my word for it. And then they formulated an equation that really surprisingly, accurately accounted for not every kind of neuron you find, but really for typical neurons that they studied, to the degree that people were given the Nobel Prize for this very phenomenological equation. And because people were absolutely convinced that there was an element of truth in there. Okay, good. And now we are 50 years later. 50 years later, we know the structures of these ion channels, and the equations make absolute sense to us through these polynomial terms. And we also know that the solution of the Hodgkin-Huxley equation lives really in a two-dimensional manifold rather than in a four-dimensional space, and so we can now analyze it. And now, when we stretch it out, we are replacing this one by another equation that is likewise phenomenological, and that captures the solution behavior of the Hodgkin-Huxley equation. That's called the FitzHugh-Nagumo equation. And so the FitzHugh-Nagumo equation is very practical in the classroom, but not only, also in research. It has been used a lot too, because now we have it all. We have the simplest mathematical equation that captures what the Hodgkin-Huxley equation gives as result. So it might be nicer to deal with a simpler equation rather than take the full equation. Okay, so now let's write down the equation. So this equation, did I take the wrong? Oh no. So this equation looks as follows. X1 dot is equal to C times x2 plus x1 minus x1 cubed over 3 plus z. And x2 dot is equal to 1 over c times a minus x1 minus b x2. These are phenomenological equations. They don't describe all kinds of neurons, and but some well. And I can even tell you that the values you can take for a and b are the following values. So we don't want to dilly-dally around with all kinds of things. This one is a stimulus parameter that tells us how much stimulus we get at the point where we drive the system, for example, at this point. So we will see what the z is doing later. The moment we just say it's another variable that is important for the characteristic of the system. So now, in how far are they similar to the Hodgkin-Huxley equation? And to see that similarity, we ask ourselves the following question: what are the curves that are characterized so x1 dot is 0 and so x2 dot is 0? Now, this is actually a trivial thing sort of to ask, but it's actually quite important, because when we look at the Hodgkin-Huxley equation, then we find that in the remaining variable, namely n and v, this one is a fast one, and this one is a slow one. So this one goes pretty fast, the v, and the n is sort of the slower guy. And so now if we take x1 dot equals 0, then x1 is usually the fast, except on x1 dot equals 0. There is slow, because the rest x2 is always sort of slow. And now x1 dot equals 0, it happens where the voltage is not changing. And so that's where the solutions are slow. Whereas everywhere else they are fast. And so if we solve this, then we are getting, then we find that x1 dot equals 0 gives us a cubic equation. We can write it as x2 is equal to, so we can put c, we can divide it out, and we are getting this one is x1 cubed over 3 minus x1 plus z. So z lifts it, and now you, at least when I was a high school student, I had to discuss these kind of curves. I was like, ooh, all my friends. That's the only reason why I, as a nerdy kid, had any friends. I could do these kind of problems, and all the other kids couldn't. So they came to me, and then they invited me to the parties. Otherwise, I would have had no girls, no party, nothing. But that rescued me. So this is what you're getting, this kind of polynomial cubic curve. For x2 equals 0, x2 dot equals 0, we are getting just a linear curve. We are getting, you know, some x2 is some a, I don't want to use other, gamma x1 plus delta. You figure out what gamma and delta is. And so, so that's what we get, and it's a curve like this. It's a line. So this one is x2 equals 0, and this is x1 dot is equal 0. Now on top of here, when you look at it, actually I should do that even correctly, sorry, I just do what I get here. So I put this one equal to 0, then I'm getting there x2, I'm getting x2 times b is equal to 1a over b minus 1 over b x1. It's important because for large x1, x2 is this, I always see that for large x1 this is negative, and so at this point it's 0, x2. For larger it's negative, and for smaller it's positive. And so if you now look, here we are not changing x1, this is x1, this is x2. So here we are not changing x1, so the motion exactly on this curve goes like this. But now on this side of this curve here, we are going up, because you can convince yourself this one is positive, and here we go down. And here, if you look here, you find likewise, here we go to the right, and here we go to the left. So you see some kind of motion around, and this is actually an behavior that we get here that has nothing to do with classical mechanics. The force that we have here effectively driving the concentration is not coming from a gradient of a potential. It's not rotation free. In fact, there is really rotation in there. Okay. At this point here, we have an interesting point. At this point, we have 0 force. if we go to this point exactly, x2 is 0, x1 is 0, nothing is changing. You call that the fixed point, the fixed point. And so here we are not moving. And now we ask ourselves, we call this point then x1 0 and x2 0. Okay, so now we ask ourselves, how do we move near this point? The way to do this is that we are expanding our equation around fixed point. So we just expand it, and if you do this, you can convince yourself that you're getting x1 dot, x2 dot, is equal to, you're getting a 0 of the forces that are at the fixed point, there's nothing, and now you're getting linear forces from the Taylor expansion that go with delta x1 and delta x2. And the delta x1, these two terms of a 2 by 2 matrix are just the Taylor expansion terms of this one expanded in x1. So if we take the derivative here, we're getting here delta x1, and here we're getting minus x1 squared delta delta x1. So this guy here gives us a contribution c times 1 minus x1 0 squared. This guy here gives us a c. This guy here, the one with the x1, gives us a minus 1 over c. And this x2 gives us a minus b over c. So this is how the metric looks like. So we have a differential equation, linear differential equation, and we all know how to solve it. If we call this matrix O, or maybe I call it M for matrix, then we look at M, we try to solve M times V12 is equal to lambda 12 V12. So we can do that. And the M's and the lambdas, lambda 12, are equal to the matrix elements M11 plus M22 over 2 plus minus square root of M11 plus M22 over 2 squared. And then minus determinant of this thing, I remember, maybe minus 4 determinant, I don't remember, who could be 4 or whatever. You can write it down, you find out what it is. So you can write it down very, very easily what the eigenvalues are. And the V's are the eigenvectors. Now, since this matrix is not symmetric, C minus 1 over C, the eigenvectors are not orthogonal. The eigenvectors are, if this is our point x0, and we draw here the eigenvectors, they could be clearly pointing in this direction. So maybe this is V1 and this is V2. So they are not orthogonal, but still we can write the solution. Maybe I call the solution here. Okay, so we can write the solution delta x of 1 of t and delta x2 of t. I can write it as V, also, you know, we need some constants here, some Greek letters. Help me with Greek letters. Mu1, V1, e to the lambda 1t, plus mu2, V2, e to the lambda 2t. And now you see that if we put t equals 0, then we are getting here delta x at 0. And this is a very straightforward equation you can solve. It's a linear equation. This side is known. You know, you assume you know where things were at time 0. You can determine the coefficients. So very, very straightforward little linear algebra first months. Okay, so you can write it. Now, however, you have some interesting possibilities. For example, you can have the possibility that this one here is larger than 0, the radicand. And then you're getting a real eigenvalue. And now you can have it positive or negative or mixed. If it is positive, then you are getting this kind of motion. Wherever you are, you're going in the direction of the eigen. If you're on an eigenvector, you're going away from it. And if you're in between, then it is in between, and how fast you go depends on the eigenvector that goes with a particular eigenvalue. So you can imagine it. If it is both negative, so this is positive, positive. If it's both negative, you're going towards the center. Negative, negative. You go this one unstable. This one you call stable. You have a stable point. You go home there. And if you are mixed, plus minus or minus plus, then one direction goes away. One direction goes towards. You call this a saddle point. So like in the saddle, you can, in the saddle, you can forward, backward. Even I can ride the horse, but when it comes to this direction, I fall off immediately. That's unstable. And now you have the same for the case that you have here, negative value. Then you're getting conjugate complex pair of eigenvalues plus I omega minus I omega. And when you are looking at the solution of a value, very famous equation is x1 dot, x2 dot is equal to 1 over 2, 1 minus I, e to the I omega t plus 1I e to the minus I omega t. What is this when you write it down? The first one is cosine omega t. The second one is minus sine omega t. That is a circle equation. So here you go on a circle. So they describe circular motion, or rather in general elliptic motion, going around the point. And if this real part of the eigenvalue is positive, you go away from it. If it's negative, you go towards it. And so now we have then the following kind of behavior. We either go towards this point. So I draw like as if these, you call them singular lines, and if they are eigenvectors, but of course they are not. You go towards some point, they are stable, or you go away from them, or halfway, and that's when it's real. And when it's not real, when it's complex, you go like this, when it's stable, or you go like this, when it's unstable. this look complicated. No, it's not complicated. But it reminds me, if you want to solve it, it reminds me of my childhood. In my childhood, I didn't like to eat my plate. I always played with the food, but my parents were very strict with me. They had to sit there, finish your plate, finish your plate. They brought me up totally wrong. For modern, would have been better if they tell me, no, don't finish, only eat when you are hungry, otherwise don't eat. But that was not how you were brought up in those days. So I had to finish my plate. Oh, I played with it. And most interesting was when we had pasta. So then you can really play a lot. And I learned about the solution of this equation because when you solve this equation, these are the equation, this kind of solutions, one solution, other solution, cross each other, not allowed. Pasta on the plate cannot cross if the pasta is a solution, because at this point you have a unique solution. When you go here, you go deterministic in one direction, you don't cross. You have this crossing in classical mechanics because you have position and momenta as variables. You always forget the momenta, but they are also independent variables. That's why you can cross trajectories here, no. So when you play here with the solution, and you want to see all the solutions, it's like playing at a kid with your pasta, but the pasta have to all lie on the plate, no crossing of the pasta. Now, I wasn't that smart as a kid. I don't want to make up stories. But you are smart. You can convince yourself that the pasta picture here, the following, that when you go away, the pasta goes towards this area. So when you go far away, you have actually an attractive force. So it's not like the pasta can go to infinity. No, it cannot go beyond the plate. The forces are there inside. So now you have your plate, you have to move your pasta around. You cannot go outside of the plate because the forces go inside. But let's say you have an unstable point. So what do you do when you have the unstable point? There is a solution, however, not with real pasta, although pasta comes in all kinds of thickness. Now you have to imagine that you have pasta that can become infinitely thin. Because the solution is that somewhere here, now I cheat already a little bit by putting something in here that is not so clear yet. There is a line that you call the limit cycle, and all your pasta goes like this, like this, like this, like this, like this, like this. And here it goes like this, like this, like this, like this, like this. And everything goes to the limit cycle eventually. So the pasta goes around the limit cycle. But not so simple. This you can do very nicely with a computer. You find that here is a valley. All the pasta goes into the valley very fast and then slow, because this lies on the slow manifold x1 dot equals 0. All the pasta goes here to this valley that ends here. And in between here we go sort of parallel. But we go, eventually everything goes to this, what is called the limit cycle. So we go round and round and round. So this is how the system behaves. And that is what we need to understand when we want to understand how nature designs these channels. The next time we are talking to the end of the story, but here I still have, a minute, and I want to use this minute for a very important and sort of like a deep thought. So basically, I brought this up already last time. Basically, life has to use physics, it has to use chemistry and physics and obey all the laws, but it has a purpose. It wants to survive, it wants to recognize what is going on around the world around it and respond. So it wants to use physics to realize an algorithm, to realize how can I make a decision. And that's what the neurons are for. How can I compute a decision? And so basically it wants to develop an algorithm that helps it to survive. And here we need an algorithm for a neuron to make a decision. It integrates signals from other neurons and has to now decide at some point, should I tell the other neurons about it? Or is it just some stupid noise that came here? And when we look at these solutions, that's what we do next time, we'll see that here we're getting actually exactly this threshold behavior. The system will behave like when we are below a certain threshold, which is this x1 variable is the voltage. When we are below a certain value, we quickly relax back and nothing was there. But when we just go a little bit above a threshold, then boom, we're getting a huge signal. Then we go down, we return back to normal, to the resting value. And whenever we do that, we are getting the same signal. It's not like sometimes twice as big, no. So either when we are below the threshold, we relax back to the stationary value. When we are above the threshold, we are getting the same signal, and we return. And so nature had to learn how to use molecules to realize such behavior. And it wasn't like a straight route to do this. It was a little circuitous. It had to actually put several of these channels together in a kind of togetherness and cooperation that is described by the Hodgkin-Huxley equation. So nature had, billion years, that's a long time, like how long my class takes here, now billion years, right? So you had a long time to figure things out. And it figured it out in a quite an amazing way to get rise to this kind of behavior. We are not there yet. Next time I tell you, and you will really see how beautiful and how clean it is, and that we are getting really this nice threshold behavior. But the point is that you realize the relationship between the hardware, which are the channels that nature can design, and the software, which is in this case, not just the physics, but rather the mathematics of the kind of equation that gives you overall the right behavior. And the very typical aspect that we see here is actually the nonlinearity of the equation. So if you're just a linear equation with, this would be on a linear term, it will all relax to some value, not much happens. But since we have a nonlinear equation, we get much more exciting behavior. We get switch behavior, logical gate behavior, and so on. And so that is really the difference that's really the difference that nature discovered. Polynomial terms that permitted to shape out of these systems the behavior that is digital and lets even a noisy system compute with precision. We will actually even add noise to this, and we will always get basically still the same kind of signals, just a little bit wiggling, but if you look at it from a distance, it looks exactly the same signal. Okay, thank you very much.